Okay, everyone, let's do this question 3 from the June 2021 paper 2 for CSEC physics, okay? So this question 3 is about waves, right? And they're saying here for part A that waves can be described as either transverse or longitudinal. And they want us to, first of all, explain what is meant by a transverse wave. Now, a transverse wave is one which has vibrations that are perpendicular to its direction of motion, right? And a transverse wave is characterized by crests and troughs, right? So if I were to do a quick sketch of that, just for completeness here, we have our rest position here. This is the direction of motion of the wave, right? And with transverse waves would be up and down, up and down. So that's how the vibrations are, right? So the vibrations are like up and down from this rest position. And so we have these regions here that we would say that this is a crest, right? And this region down here would say that this is a trough. And then this is a crest. And then we're only showing two crests here and a trough here. Right, but this is a transverse wave. This is the motion, the direction of motion here is up and down, perpendicular, right? To the direction of motion of the wave, and the wave is moving in this direction. So that arrow there is the direction of motion. And so the vibrations are perpendicular to that, right? And by that, we mean that if you imagine this being a fixed rope, and we're just going up and down with the rope, we are, that's a transverse wave that's generated, right? So it's a transverse wave. The vibrations are perpendicular to the direction of motion, and a transverse wave is characterized by crests and troughs. So this peak here is like a crest, and then this inverse peak is what we call a trough, okay? So all of that for 3 marks, and we're good to go. Okay, so moving right along, they're asking us to give one example of a transverse wave, right? All electromagnetic waves are transverse waves. So we could maybe even just zero in and say a light wave is a transverse wave, right? But let's just recap and just know that all electromagnetic waves are transverse waves, right? So we just pick one. A light wave is a transverse wave, and that's good for our 1 mark, and we're moving right along, right? So move on to part B now of this question. It's asking us to define the term ultrasound. So what is an ultrasound? Well, an ultrasound is a sound wave which has frequency above 20 kilohertz, right? Let's just say what the other ones are. If it was an infrasound, or we're in the infrasonic region, that would be what? That's less than, what is infrasound? That's less than 20 hertz, right? And then our audible region, what we can hear, audible region would be between 20 hertz, right? And 20 kilohertz. So that's what we as humans can hear. We hear in that audible region, and then now ultrasound would be above that, and that's what we're defining here, right? We're saying that the ultrasound region is when we are above that 20 kilohertz, right? So our definition here, an ultrasound is a sound wave which has frequency above 20 kilohertz. So that's this region here, okay? All right, so we're moving along. Let's see. So that's for 2 marks, and I think that we would be good for those 2 marks. We stated the frequency range, and I think that's very important. And we also stated that it's a sound wave, so I think we're in good shape for those 2 marks there, okay? All right, so moving right along. The next part 2 of section B is asking us to state one example of the application of ultrasound. So one example of the application of ultrasound is in diagnostic imaging, right? You know, we use that in prenatal scanning to look at a baby, you know, a baby that's growing. So we can use diagnostic imaging, ultrasound in diagnostic imaging in that way. And we can also use it in the cleaning of small electronic components. So because the ultrasound is at that high frequency, what we'll have is that there's a lot of vibration, and we can remove dirt and any trapped particles from small electronic components, right? So really you only had to list one, but I just threw an extra one in for fun, you know? But we just really have to state one example, and we can just say it's using diagnostic imaging, and we can get specific and say if we want to do some prenatal scanning, or if we want to examine internal organs, you know, we could use ultrasound to do that. So that's all in diagnostic imaging, okay? And that's just 1 mark, so we're good, right? Okay, so moving along to part C of this question. So it's saying that figure 3, so this is our figure 3 here, this whole thing. It shows the path of a light ray going from air through, so it's going from air through a cube of ice, along with 2 rays showing partial reflection, okay? All right, so that's what this figure is showing us, right? So that's our figure there of light going from air into ice. So they're asking us first and foremost to determine the angle of incidence on the face MN. So this is our face MN, and they're asking us to find the angle of incidence. So at what angle is this light ray hitting up on this face, right? So we can see that from their diagram there that they gave us, that this is our point of incidence here, right? That's the point at which it strikes that MN face. And right at that point, you see that they've given us a normal to that right there, right? So we have our normal and we have our incident ray. And so the angle between the normal and the incident ray is our angle of incidence. So this is our angle of incidence, right? And this is what they're asking us to find, to determine in this first question here. So in order to do that, we know that the total angle here is a 90-degree angle, right? This whole thing is 90-degree. And they told us that this angle that's right here between the face MN and the incident ray is 31. And so we need to find this angle, which is our angle of incidence. And so to do that, we do 90 minus this 31 to get us this angle. And that number ends up being 59, right? So 59 is our angle of incidence. So that's what I've shown down here, right? That 59 is what we end up with. We subtract that 31, that's this angle here, from our total angle of 90, right? And so we get 59, and that's our angle of incidence. Okay, so that's for 2 marks. We're moving right along. So for part 2, they're asking us to calculate the angle of reflection now on the face MN, right? So let's go back up and look at MN and look at that angle of reflection. So the angle of reflection is this one right here, right? So once we have this incident ray here, it comes and then it's just going to be reflected back, right? And based on our laws of reflection, we know that whenever reflection occurs, our angle of incidence is going to be equal to our angle of reflection. And so in this case, this is our angle of reflection. Our angle of reflection is going to be, this one right here. It's between the reflected ray and the normal. So it will just be this one here. And so our angle of incidence was 59. So our angle of reflection, I'm going to write it as theta reflect, right? It's going to also be 59, because based on the laws of reflection, our angle of incidence is equal to our angle of reflection. So that's this angle here, and they're both equal, right? So theta incident is equal to theta reflection. And that's from the laws of reflection that we know that. So since we already calculated theta I, we can say, okay, it's the same thing. So theta reflect is also 59, okay? All right, so moving along now. Moving right along. we just write that in there, and you see that that's 1 mark because they expect us to just see that immediately, right? We're applying laws of reflection. If I just calculated the incident angle, and I know that the reflection is going to be 59 as well. Okay, so 1 mark, we're good. Okay, so for part 3, they're asking us to calculate the angle of refraction at the face MN, given that the refractive index of ice is 1.31. So let's just scroll back up and look at that picture again. So this is our face MN, right? This is our MN face. We have our incident ray coming in. And once there's a change in medium now, guys, it's a change in medium that's taking place. We're going from air, which is a less dense medium, and now we're going to ice, which is more dense. So this incident ray, it comes at this point now, it's at this boundary. It comes into this more dense medium, which is ice. And so when we go from a less dense to a more dense, you know that that ray is going to bend towards the normal, right? So we see that this ray is kind of like bending slightly towards this normal. And so this here is going to be our theta R or theta reflection. So let me do theta refraction. So let me put refract beside that. And so it's refraction because we're changing medium, right? So that's theta refraction, right? So this is the angle that they're asking us about. It's the angle between the normal and the refracted ray, okay? So when we think about refraction in this manner as we're changing medium, the first thing that should come to mind is Snell's law, right? So Snell's law is what we're going to be using here. And Snell's law just say that the refractive index is equal to the sine of theta I, the angle of incidence, over the sine of the angle of refraction, right? And so we're going into ice. That's our second medium, and our first medium is air. And so we write the refractive indices, their ratios this way. And so what we have to do now is, because we're trying to find theta R, which is our angle of refraction, then we just really rearrange everything to make theta R the subject, right? So when we do that, or however in it here, I've plugged in the values that we know for theta I that we calculated is 59. So I just put that here. Theta R is still unknown. We don't know that. And they told us that the refractive index of ice is 1.31. So we're going to put that here. And we know the refractive index of air is 1. So we put 1 here, right? So now we're going to transpose to make theta R, sine theta R the subject, because that's what we want to find, right? So to do that, we do cross multiplication, 1 times sine 59. That's what I've written here. And then over here, we have 1.31 times sine theta R. So that's what I've written here. And then now we make sine theta R the subject. So to do that, we end up with sine theta R being equal to 1 times sine 59 divided by 1.31, right? Perfect. So now all that remains is that in order to get out the angle, we have to do the sine inverse of both sides. And when we do that, we end up with theta R over here, and then sine inverse of this value that we would have calculated here, okay? And that value ended up being 0.654 in the parentheses. I did the inverse sine of that, and then I got theta R, or my angle of refraction, being equal to 40.8 degrees, right? And that's for 4 marks. So really, whenever you see a question like this, where they're asking you to find the angle of refraction, right? And they give you a refractive index of a second medium, then you know you have to use Snell's law. And so this is effectively Snell's law that we've written here. It states that the refractive index is the ratio of the angle, the sine of the angle of incidence over the sine of the angle of refraction. And we can just rearrange this and plug in what we know to find our theta R, and that's exactly what we did here to get 40.8 degrees, okay? So that's for 4 marks. So pretty detailed. Make sure that you have a good grasp of this and you understand how to apply Snell's law, okay, to find an angle of refraction. So moving along, for part D, the final part of this question is they're saying that on the diagram that's shown in figure 3 on page 11, label the critical angle theta C for ice, okay? So let's go back up and determine which one is with the critical angle. So we're in ice now, we're in ice, And what's going to happen now is this rays are going to be our incident ray. It's going to be incident on this face, NO, as the ray tries to leave from ice to go back to air. So whenever you see a critical angle question, just think, we're going away from a more dense medium, ice, to a less dense medium, which is air, right? So effectively, this ray that was previously our refracted ray is now becoming our incident ray. That's going to be incident on this face as it tries to exit, right? And so you see we have a normal at that point as well. And what you see here is that the refracted ray in this case actually ends up just grazing along this face NO. It just grazes along the surface. Ordinarily, you would see it maybe out here, right, in the air. And what it would be doing is, because you're going from a more dense to a less dense medium, it would be bending away from the normal in that case, right? So it would be bending away from the normal. So perhaps we would draw it here first, bending away from the normal, and then it keeps bending even more. So until it's like completely just grazing along this surface, right? Once it's grazing along this surface, we say that we're at a critical angle, because now the ray is no longer out in this less dense medium. It's not refracting in the less dense medium. It's grazing along the surface. And then eventually, if this critical angle is large enough, it will end up being totally internally reflected, as this arrow shows here, right? But since the question is asking us about the critical angle, it's just going to be this angle right here, right? The angle at which we just get some grazing of that refracted ray along the surface, right? So again, this is our angle of incidence. And in this case, the angle of incidence is the same as our critical angle, because that's the angle along which the ray just grazes the surface. It doesn't leave the ice completely. It just grazes along that boundary there, that ice-air boundary. And so here, the angle that corresponds to this is what we call our critical angle, and that's just this one right here. Right, the angle of incidence that causes this kind of a grazing is what we call the critical angle. So that's just this one right here. Okay, the angle between that incident ray and that normal is our critical angle. Okay, so that's what they want us to identify for that 1 mark. And so with that, that's the end of that question. So as usual, if there are any questions or any comments on this, definitely drop that down below and I'll be sure to clarify anything for you as needed. And I'll see you in the next video.